The objective of this video is to introduce finite element analysis techniques for calculating magnetic fields in electrical machines. When it comes to solving Maxwell's equations, we have two fundamentally different pathways that we can pursue. We can take an analytic approach, which in this class we'll view as a direct solution to the field equations, but using simplifying assumptions to make them solvable. Or we can take the analytic approach by using magnetic equivalent circuits. Both of these techniques we're going to describe in this class, and these approaches are nice because they give you physical intuition into the system. They help you understand the physics behind what is going on, and they build up your mindset as a designer and inform your decision-making process. So you start to gain an intuitive feel for the electric machine by working with the analytic expressions. So we'll be doing that a lot in the lectures. So the positive is that these build up physical intuitions that are physically meaningful. But the downside is that they tend to be less accurate because of the simplifying assumptions that we make. The second fundamental pathway that we can take is to use numerical techniques to solve Maxwell's equations. And in this class, we're going to do this by using the finite element method, or finite element analysis. So this goes by two names, like I just said: finite element analysis, which is frequently abbreviated as FEA. You might hear people talk about finite element method, which goes by FEM. And so we'll use these terms interchangeably in this class. And when we talk about these methods, we don't actually talk about writing our own code to do the numeric solution. Instead, we mean that we're going to go to a third-party tool. We're going to use a software program to do this for us. And the advantage of this approach is that it's more accurate. If we set up our solution properly, we can get very accurate results. The downside of this is that it takes longer to evaluate. And we have the garbage in, garbage out phenomenon. That is, if you don't know how to use your tool, or if you don't understand how to use the technique properly, you're apt to make incorrect settings or incorrect configuration options when you enter your model. So that is to say, you put garbage into your model, and therefore the results that your model gives you are also garbage. So you put garbage in, you get garbage out. To prevent this phenomenon, it helps to discuss what these tools are actually doing behind the scene and formalize our approach to using the tools. And so the point of this video is to open up the hood of our FEA tool and talk about how it works. This is going to help us to understand what is going on behind the scenes so that we can apply the proper settings and configuration options to get physically meaningful results out of our tool. And you're going to want to pay close attention to this because using FEA tools is a core component of this class. Our ultimate final goal in the course is to have you use an FEA tool linked up to MATLAB scripts that you will write in order to optimize the design of a motor. And so throughout the course, we'll be developing both the analytic approach to analyzing magnetic fields and calculating design performance parameters of our motors in parallel with the numeric approach using an FEA tool to analyzing the design performance of motor designs. And this is the first video in our parallel effort on the FEA front. Well, without further ado, let's get started. In this class, we're going to be talking about 2D FEA using the vector potential formulation. What does that mean? Let's start with the vector potential part. If you recall from Maxwell's equations, we had two primary laws of interest that are going to be solved with an FEA tool. And those two laws are Faraday's law and Ampere's law. And so we create the vector potential formulation by defining a vector A where the curl of that vector is equal to our magnetic field vector B. So this is a mathematical trick. A is not a physical quantity. Our physical quantity is our magnetic field B. It just happens to work out through the mathematics, through vector calculus, that we can define B, since the divergence of B equals 0, we can define B as being the curl of another vector, because the divergence of the curl of a vector is also 0. And this magnetic vector potential has units of volt-seconds per meter. So again, this is a mathematical trick. Much like the reason that we define the H field, we're also defining the A vector as a matter of convenience. You'll see in a little bit that for the 2D FEA approach, the magnetic vector potential simplifies the amount of equations that we have to solve considerably, and this speeds up our numeric solution approach. So this is a mathematical trick that we play, and to learn more about this, I would refer you to an E&M course, a fields course, textbook. But for our purposes, we can just note that this is possible, that you can have this quantity, this vector A, and the curl of which is equal to our magnetic field. And we can relate this to our H field, and we can then plug that into Ampere's law to get this equation. And this equation is the magnetostatic formulation for magnetic fields. That is, it has everything you need to know if you assume that all time derivatives are 0 if you're analyzing a magnetic field. It has a source term, which is a current density in a region, and it has our vector potential A. If we solve for A in terms of our current density, we can then get B by taking the curl of A. And so this is called the magnetostatic equation. To incorporate the time-varying components, we need to include Faraday's law. And so plugging in that B is equal to the curl of A, we get the following expression. And if you'll recall from your fields course, you can solve this now in terms of both the vector potential and a scalar potential. And we're not going to get into the weeds and what this means. For our purposes, it's useful just to see how these equations come about and what the FEA tool is actually solving. So if we take this a step further, we can recall that J, our current density, is equal to our conductivity times our electric field. And we get this expression. So we can plug this into our magnetostatic formulation, and we'll arrive at a complete differential equation that has got a time derivative for A. So if we plug both of these equations in together, we get the following expression. And this expression is our general transient vector potential equation that our FEA tool is going to solve for us. And again, when our FEA tool solves this, our unknown quantity is A, and our known quantities are our material properties, so sigma, and our material permeability, which is mu. And remember that mu is a function of our magnetic field from the BH curve. And finally, we treat this electric scalar also as a known quantity, and this is used in the FEA tools to enforce boundary conditions or to impose certain constraints. And we're, again, not going into the details of how that all comes to be. Okay, so that's the equation that it's solving, and it's solving to determine the vector potential A over our region. That answers the vector potential formulation part of this statement. Now we're going to talk about what it means to be doing something in 2 dimensions. Well, when we say that the problem is 2D, that means that we're going to assume that we have no z direction component to our fields. That means that B in the z direction is 0, and H in the z direction equals 0. It basically means that if we were to take this example motor here, this is a trivially simple example, and so what I'm drawing on here is a permanent magnet rotor inside of a stator. And I'm trying to draw this in 3D, if you excuse my drawing skills. So we've got this permanent magnet rotor inside of a stator, and our field is going to do something like this. It's going to come out of the rotor, and it's going to go into the stator, and then return through the ferrous steel back to the rotor. And you'll notice that in this diagram, we're showing that the field is completely within the radial cross-section of the machine. So if we label our axes as having a z component, a y component, and an x component, we notice that there's no portion of the field that is in the z direction, or if there is, it's very minuscule. I mean, in actuality, you will have fringing fields that will come out of the page on the top side and curve down into here. But we're not going to worry about that. We're saying that those fields are negligible, that we can actually model this machine by looking at a simple cross-section in the xy plane like this. And that any quantity that we care to calculate, such as a force or a torque, will simply scale by the axial length of the machine. So if we calculate the quantity for this cross-section here, we'll take it and we'll multiply it by our length in the axial direction to get an approximate value for the real quantity of the system. So that is to say that our 2D FEA solution of this cross-section is going to give us a torque per meter. And so if we take that and we multiply it by our axial length L, we'll get our approximate value for torque. Okay, so let's go back to this. What does 2D mean? It means that BZ and HZ are 0. It means that our end effects are negligible. Our axial effects are negligible. And it means that we only model a single XY cross-section. So I'm talking about this specifically for a 2D rectangular model. There's also a 2D axisymmetric model where you have symmetry about rotating about the z-axis, and I'm not talking about that. In this case, I'm talking about the simple xy Cartesian coordinate system and symmetry as you traverse along the axial direction. Alright, so what else does this mean? Well, remember that B is equal to the curl of A, and since BZ is 0, this means that A has only a z component and J has only a z components. So this assumption has dramatically simplified our equations. This gives us our first big plus. We could solve it in the full 3D, and to be sure, that is the most accurate thing you can do is you can solve your magnetic fields using 3D finite element analysis, but that takes a lot of time. And for our purposes in this class and for most motor designs, 2D FEA is perfectly accurate enough, and it is dramatically quicker to solve. Remember, the equation that you're solving is in this blue box up here, but by using 2D, we've set all the vector components of A equal to 0 except for the z direction. So we've got a much simpler set of equations. Instead of 3 equations, we have just a single equation. We can then calculate B and H simply from our vector potential by the following derivatives. And this just falls out of evaluating the curl of A. So we've answered the question for what 2D FEA means. Ultimately for us it means simpler equation and faster solve time, but with the possible drawback of less accuracy. Or at least that we have to carefully take into account that we're neglecting the end effects and come up with some other way to approximate them if we think that they may be important. Now let's get to the last part of the statement. We've talked about what vector potential means. We've talked about what 2D means. Let's now talk about what FEA means. We keep saying this phrase and this acronym, but what are we talking about when we say it? So the story is that solving for the exact solution of Maxwell's equations is very difficult to do for most geometry. In fact, it can be impossible in a general sense. If you're trying to take into account the nonlinearities of the steel and any arbitrary geometry, it becomes far too complicated to be a worthwhile exercise. So what we do when we really want to have an accurate solution is we somehow discretize our space and we solve it in small regions. And the idea of FEA is to come up with a set of nodes that we're going to solve our vector potential at, and then interpolate it from those nodes everywhere else. So Maxwell's equations are a set of partial differential equations, and FEA can be used for far more than just Maxwell's equations. It's used for heat transfer, for structural analysis, and so on. It's a general approach to solving differential equations. Alright, so we're talking about nodes here. Let's develop this set of bullet points by way of an example. I'm going to draw a stator tooth that you might find in an electric machine, and say that you're going to do FEA on this tooth. The first thing that we just said is that you're going to solve it at nodes. And so the nodes are literally vertices that you would place onto this tooth. And the nodes end up being vertices of elements. And you're interpolating the value of the vector potential within the elements. So the elements are what occur when we connect these nodes. And oftentimes in a 2D code, you'll have triangular elements, but you could have square elements or hexagonal elements. All of this is possible, and it's a feature that will be implemented within your tool. In some cases, you might actually be able to tell the tool what kind of elements you want, but oftentimes you're stuck with whatever the tool's mesher supports. So this brings us to our next point, which is that the mesh of an FEA tool or an FEA solution is the set of elements that you place in it. And so what I'm doing right now, when I'm placing these nodes on here and then I'm turning them into elements, is I'm meshing this geometry. And so actually the act of meshing is placing the elements, and that defines where the vertices are. We can have all kinds of different shapes and aspect ratios of our triangles, but the point is that each of the corners of our triangles are nodes, and the nodes are the vertices of the triangle where we are solving for the numeric solution of our vector potential. And then within the triangle itself, we're interpolating the value of the vector potential based on the values of all the nodes of the triangle. And so we have nodes that are shared between elements because the elements are adjacent to each other. And so we say that we have a fine mesh when we have a lot of elements, or a coarse mesh when we don't have a lot of elements. So a fine mesh will give you an accurate solution, but it takes more time to solve. And what you'll find when you're using FEA tools is that you have a constant battle going on between how fine of a mesh you want versus how fast of a solve time you want. And the question that you're always going to be wondering is my mesh fine enough? Is this a good enough mesh? And really, to answer that question, you have to do what's called a sensitivity analysis, where you keep making your mesh more and more fine, progressively more fine, until your solution result stops changing. So if you keep increasing your mesh density by an order of magnitude, and at some point you notice that you've converged to a final value of your solution, maybe you're trying to determine the total flux that's crossing your stator tooth, then you know that you've got a fine enough mesh, and you can perhaps back it down. You can make it more coarse. And the reason that you go through this tuning process is twofold. One, you want to make sure that you have an accurate solution for this given problem. But two, if you're going to design a set of motors, you might be trying to establish a rule of thumb for how fine the mesh needs to be in a certain region to make sure that it's sufficiently accurate. So we've talked about nodes, elements, and the mesh. The next thing we need to talk about is boundary conditions. And boundary conditions are needed to properly define the problem, and they also can be used to exploit symmetry of a problem in order to reduce the problem size. So there's two fundamental types of boundary conditions that come up. The first is a prescribed value of your vector potential on a surface or a set of nodes. And the second is a derivative of our vector potential along a certain direction. And from these boundary conditions, you can derive other types of boundary conditions that are implemented within FEA tools to make the problem more solvable. And that gets to this point here, that we can use it to reduce the problem size and exploit symmetry. An example of this is a periodic or anti-periodic boundary condition. And these types of boundary conditions say that the vector potential along a certain surface is the same as the vector potential along a different surface, or it's the opposite of the vector potential along a different surface. So for example, let's go back to this motor that we had up here. We can notice that in this image we have symmetry in that along this plane here, our magnetic fields reproduce themselves in the circumferential direction. And so if we pose a periodic boundary condition, we can model only half of our model. And so this will be described more later in the course, and as you work through examples using your FEA tool, you'll be confronted with situations where you have to impose periodic or antiperiodic boundary conditions in order to simplify your geometry. We want to simplify our geometry whenever it is possible to do, because by reducing our problem size, we can dramatically improve our computation speed and make our problems much quicker to solve. If we're doing a design optimization, we may be evaluating hundreds of thousands of designs, and every second that we save on evaluating a single design can pay off largely in the long run. So there are three types of finite element analysis, and we're going to consider two of them in this class. First, we have transient FEA, and that means modeling the complete equation that we wrote out up above. So I'll copy and paste this down below. So in that case, we're solving this complete equation, and our FEA tool takes this equation and the mesh that we set up, and it constructs a set of coupled ordinary differential equations in time in matrix form. So we end up with a set of equations that looks like this. By n, where we have n nodes in our solution, in our mesh. So you come up with a mesh, it has 100,000 nodes. That means that you have a matrix C and a matrix K that are size n by n. And that means that you have this vector A dot and A that have n rows to them, because A dot is our vector potential, is the value of dA dt at each node. And A is the value of our vector potential at each node. And on the right-hand side of this expression, we have another vector, which is constructed from a combination of our boundary conditions and the source terms that we load into our solution. So what are source terms? Source terms are the current densities that we assign, they're the magnets that we assign, they are the excitation for our motor system. So in other words, if we talk about this in terms of knowns and unknowns, we know the value of our source term, because that's what we set up, and we know our matrix K and C, but we do not know our vectors A and A dot. And I should point out that our matrices K and C depend on the mesh that we're using. They depend on the material properties, which means that they're nonlinear. They depend on the saturation state, since mu is a function of B. Okay, so we've got this set of ODEs that are differential in time, but they're discretized in space. And what your FEA tool does is the following set of steps. It discretizes this in time. It's already discretized it in space. That's what the mesh did. And now it will discretize this in time using a so-called time marching algorithm, such as forward Euler or backward Euler. And to do this, you have to specify for the algorithm a time step size. Next, it will invert these matrices to solve for your vector potential at each time step. So it will have a numeric technique to take matrix inverses, and these are very large matrices. Remember, they're size n by n, so it has a lot of work to do to invert it. And they're also nonlinear, which means that there will be an iterative approach to solving this set of equations. So for the iterative approach, you'll see something like Newton's method, and you'll see a wider range of methods to invert the matrices. So that's transient FEA. We like it because it models the complete physics. It's the most accurate. You have your time dependencies within it. We are critical of it because it can be slow, because you're marching in time. Maybe you're taking 400 time steps per revolution of your rotor. Just like your mesh size required a sensitivity analysis to determine if it was fine enough or not, your time step size is also subject to you doing some kind of sensitivity analysis to determine how fine it needs to be. So that's approach number one. That's the most complete approach. Approach number two, which will be a particular focus in this class, is static FEA. And in this case, we take our same vector potential formulation, but we get to neglect all the time varying terms. So we actually go back to this equation that I labeled up here as being our magnetostatic formulation. And in that case, our set of matrix equations becomes the following, which means that we have no time steps required. There's no time derivative here. We do not need to discretize this in time. And so the obvious advantage of this is that it's fast. But the disadvantage is that we neglect the time-varying component of Maxwell's equation. We neglect Faraday's law. So it is less accurate because we have no induced electric fields, which means that we have no induced currents. At first, this may sound like a pretty major problem. However, as we'll see in the class, there are various techniques to make this work fairly accurately. In electric machines, oftentimes we don't want to have induced currents within the bulk of our material anyway. We take proactive design action to make sure this doesn't happen, so we'll use laminated steel so that we can't get eddy currents appearing in our steel. Or, we have current flowing in the coils of our machines, but oftentimes we will prescribe that current. That will be an input to our FEA method, and it is not something that we have induced. And the third approach is called the time harmonic or eddy current solver. In this case, we take the transient equations, but we assume that all of our sources are sinusoidal, all of our sources and solutions. So we assume that our vector potential is sinusoidal in time, as well as our current density. So if we plug this expression for A into our transient FEA formulation above, we get the following expression. If we take this expression and we divide both sides by e to the j omega t, we're left with a formulation that looks quasi-static. It looks like that static solution that we had, the static formulation that we have above. Now, a couple things to note. One, I've replaced mu with mu effective. This is magic. Different FEA tools will take different approaches to this. The problem is that mu is nonlinear when you have a ferrous material. When you have silicon steel, we've been talking about BH curves. But the whole premise of using phasor analysis, of using this time harmonic solution, is that your solution is linear. So what your FEA tool will do is it will have some kind of magical algorithm to determine an effective permeability. And the details of this are important, and you have to refer to the help documentation for your tool to understand what is going on with this. We'll talk more about that later in the course. The second thing I want to point out is that this equation that we have up here is intended to solve our solution at a specific frequency of omega. So if we want to sweep the frequency, if we want to evaluate our solution at different frequencies, we have to do a bunch of separate solves for each value of omega. And so we can say that this solution approach looks static for any given frequency. It's a steady state solution. And if we review it, we can say that the pros are that it's fast, just like the static solve is fast, and that we can model time-varying fields and induced currents. However, again, the challenge is that it's less accurate than our general transient solution, and this accuracy problem primarily comes from the fact that we've had to linearize our material, so that effective permeability. So we've talked around what FEA is and the formulations that are used to state the problem and solve the problem. Let's now briefly talk about the workflow for using an FEA tool. And the workflow is as follows. So first we have to enter our geometry. We have to draw our problem within the FEA tool and assign the materials and the currents onto the geometry. And you will get a lot of practice doing that in this class. Second, we have to assign boundary conditions. And third, we need to set up our mesh settings. And then we hit the go button. That is, we have our FEA tool do its magic. It will mesh the problem, and then it will solve for our vector potential. And finally, we need to interpret our results. So we enter what's called the post-processing portion of our solution. We post-process our solution. And in the post-processing portion, we calculate our magnetic fields from our vector potential, and the FEA tool typically does this for us, actually. And then, because we're evaluating an electric machine, we presumably have some performance metrics in mind that we need to calculate in order to determine if this is a good design or not. And we calculate that from our magnetic fields. And these performance metrics will be things like forces, torque, on the shaft. It might be losses in the machine. It could be inductances, power factor, reactances, you name it. You have to define that, and you have to implement how you're going to calculate that, because the FEA tool does not know what you care about. We will be using scripts to do all of this. So MATLAB scripts, Python scripts, you write the scripts and you programmatically set it up so that you can repeat this process over and over again to evaluate a set of designs and determine which design is the best. This whole set of steps here, we're going to be building up to you creating MATLAB scripts to operate your FEA tool in an automatic fashion. We'll start by having you use the FEA tool directly, and then you'll progressively develop a set of functions and scripts that will be able to run this for you to evaluate a set of designs in a batch mode. Okay, let's summarize. In this video, we have introduced finite element analysis for calculating magnetic fields in electric machines. We've talked about the fundamental different paths for evaluating Maxwell's equations within an electric machine, and this lecture is focused on the numeric pathway, primarily through finite element analysis techniques. We've defined the formulation that's used, that the FEA tool is solving, and we've talked about what it means to solve in 2D versus 3D, and what it means to use the finite element method. We've defined nodes, elements, meshes, boundary conditions. We've talked through the different types of FEA solutions, and we've commented that in this course, we're going to be focusing primarily on static and time harmonic solutions, and then we'll be using post-processing features in order to calculate our full set of performance metrics. We've walked through the workflow to evaluate a design in FEA.